Okay, welcome to the first video about random variable. And in this video, I will provide you about the motivation of random variable and what is a random variable. I mean, the definition of random variable. So, um, in definition 1.3, we have, if f is a sigma field on omega. In this phrase, I didn't talk about the probability space yet, so I just talk about F is a sigma field on a set omega, and then a function or a mapping psi that map from omega to R. We call it is F measurable if the set of psi belong to B is belong to F. It means that it is an element of F. So this is the short form, and in remark 1.1, we provide you about what is the full form of this set. The full form of this set, it means that the set of the small omega belong to big omega, such that psi of the small omega belong to B. B here it is the subset of Borel set that I talked about Borel set in the third video already, and this set have to be belong to F. Then the mapping psi is called F measurable. So yes, the mapping psi is called F measurable. So if we talk about probability space, in probability space that we have omega is a sample set, F is a sigma algebra on omega, P is a probability measure, then this kind of mapping psi, which is F measurable, we call it a random variable. It means that a random variable in a probability space is not just a mapping that map from omega to R, but it also have to be an F measurable function or F measurable map, something like that. So I will provide you a simplest example. For example, in the experiment of flipping a coin for one time, and the result of sample set is equal to h and t, and the power set of omega is defined by this. So if I set a mapping psi that map from omega to R, which is satisfy psi of h equal 1 and psi of t equal 0, we cannot say this is a this is a random variable yet. We have to check the set of uh, omega belong to capital omega, that psi of small omega belong to the subset of Borel set is belong to F like this or not. And the small omega here can be H or can be T. So we have to check if uh, if this set is belong to the sigma algebra, then we can call a mapping psi is a random variable. So now we go to talk about the motivation of random variable. Oh, before I go to the motivation of it, I want to tell you that this is the probability space omega f p here, and if we want to visualize the probability of an event again its domain, we know that the probability measure in the second video, it is a mapping from F to 0, 1. So if we want to visualize, if we want to plot a graph, okay, that the horizontal line is f sigma algebra, and the vertical line is p, and uh, if we talk about f, it is the set that contain all the subset of all the subset of the sample space omega. And the element of f can be anything which is not necessary to be the real number. So it is hard to visualize the probability of an event against its domain if the domain is not a real number. So that's why we like we create a random variable, the concept of random variable, that at the first step, the random variable psi is mapped from a probability space, which is an abstract space. Okay, abstract space to the real, that to the new probability space, which is omega. Here it is equal to n, and the sigma algebra, instead of working on any sigma algebra, in this case we work on Borel sigma algebra or Borel set of n, and the new measurable we denote it by px. So uh, the role of the random variable is mapped from the abstract probability space to the new probability space that are, the domain is the real number. So you will question that what is the probability measure px in the new space. So in this case, px of B. For B, it is the subset of the Borel set. Px of B here, it is equal to the probability of the set, this one, this set. That in this side is the set, like psi belong to B here. Okay, maybe it's not so good. So I rewrite it. The new probability measure px is equal to p, which is the previous probability measure in the abstract probability space, and px of b, which is the subset of Borel sets, is equal to p of psi belong to b. So in this case, we know that P, the probability space P is a mapping that map from F to 0, 1. It means that the domain of it have to be the sigma algebra. So that's why the the definition of random variable, the necessary thing is that we require psi belong to B, this set have to be F measurable, have to be belong to F. It means that this set have to be, it means psi have to be F measurable, because we map from the abstract probability to a new one. So a new one, it is the probability on the real number. So after we get this, and we can visualize the probability p here, again, its domain, but in this case it is a real, a real value function. Ph, it is a real value function because the domain of ph, it is the real number, it is the subset of real numbers, so it's easier to visualize it, to plot a graph of it. And in this case, I want to connect to the definition 1.6, which is talk about every random variable psi that map from omega to r give rise to a probability measure, p psi. Oh, uh, yes, it is p psi here. It is px in. Sorry about that. It is px. Yes, but okay. P psi of B, where B here it is the subset of Borel set that equal to P of psi belong to B. So in this case, on A defined on the sigma field of Borel set B belong to Br. And in this case, P psi, it is, we call it the distribution of a random variable psi. And from p psi also, we get a real value function. That's why I talk about real value in, yes, in the previous part, because from p psi of B, we get a real value function that defined from A, I mean that map from A to 0, 1, and f psi of H is equal to here. So from this, we get this. And f psi of it here, maybe you know already, this one we call it cumulative distribution function, or CDF for short, is a cumulative distribution function. Distribution function, or we can call it for short CDF, of the random variable psi. Yes, and sorry for the notation, p psi and ph, yes. And totally, the goal that we create the concept of random variable is we want to find the real value function that we, I mean, easier to plot or to visualize the graph of the probability against its domain. So this one, I mean, it is the motivation of random variable. Okay. Thank you very much, and see you for the next video.